Hi everyone, this is going to be a video about the work of Maryam Mirzakhani. She is the first woman who received the Fields Medal. The Fields Medal is one of the most prestigious honor in mathematics, and she works at the Stanford University. Let's first go over some of the preliminary stuff, and it's about Riemann surface and what is a Riemann surface. And one answer, a short answer, it's a little longer than the two words Riemann surface, is one-dimensional complex manifold. It reveals its a little bit of nature. It's really about the complex numbers. One-dimensional means it can be parameterized with one complex variable. So that's one description. So rather than giving a formal definition, I'd like to give these examples. So the first example here is given by z plus w equals 1. So if we replace that C2 with R2, which is xy plane, x and y being a real number, this is identified as real line with a slope -1 in xy plane. If you look at this equation, that's going to be a circle. If you look at that equation, that's some sort of cubic curve with this slanted asymptote around it. So this you can visualize how these things looks like geometrically. But what we have here is not R2, it's a C2. Let's think about that part. So C is here. The 1C can be visualized as a two-dimensional vector space. 1 representing real number multiplied by real number. I is an imaginary number multiplied by real number. By using that, we get to all the complex numbers, but not just one complex number. There's another complex number here, so we have exactly the same copy. Z takes up the two-dimensional space. W takes up the two-dimensional space. If you add these two numbers, this one is sitting inside four-dimensional space. So we visualize complex number with these real vector space as a real vector space, and it happened that this thing we have created is sitting inside four-dimensional space. So it's not easy to visualize what's in there. So following is an idea of how to visualize this thing that we created that is sitting inside a four-dimensional space. So here's an example, z plus w equals 1. The idea is using complex analytic map that is 1-to-1. So let's look at the next slide. Is this idea, complex analytic 1-to-1 map. So this is a complex number, so you choose one complex number and think about sending it to itself. So this one map, nothing happened, boring map. And the other one is 1 minus s. Think about it, you have s and it becomes 1 minus s. So here's the map. If you have one complex number, then it's mapped to s comma 1 minus s. And I'd like to claim that this one is inside this big surface, s. We call it the Riemann surface. So anything that has these two coordinates complex, if you add them up, it should be 1. So here's s, whatever that s is, 1 minus it, if you add them to this, add these two complex numbers, becomes 1. So no matter what s is, this thing is always sitting inside there. And it is easy to verify that this is 1-to-1, and individual components are given by complex analytic function. So just like in the homeomorphic case and topological case, we want to consider other directions as well. So here it is. We start with the pair ZW that satisfy this equation, and we want to identify those ZW inside this full complex structure, not just looking at S itself, and this helps us to visualize this complex structure in here. So what is a map? If we have Z and W, the reversing map of what that I just explained is ZW going to Z. So in this world, you can describe it like this. We have two, f of ZW, these Z and W are two complex variable here, and you send it back to Z. So not only this map makes sense, it makes sense in this C2 level, which has a full neighborhood of complex numbers in that two-dimensional complex spaces. So this is analytic map. The bottom line is that we created one from the full complex number analytically in 1-to-1 fashion into that object that we can't see, but this the other way around also the inverse map is also holomorphic, so we call it biholomorphic structure. So we can't really see this one, but having constructed this biholomorphism that we believe, although we deformed the metric in there, we're going to talk about the metric later, it at least preserved something more than the homeomorphisms. So if you can't see this, using biholomorphism, kind of replace it with a represented thing here. It kind of preserves this holomorphic or analytic structure. Okay, here's another example. All I change is this power to raise to the second power. We can look at it in two different ways and we compare these two things. So we do the same thing. You try to isolate one variable in terms of another, and we have a problem this time. There's a square root business. One thing is called positive square root, the other one is negative square root. And it is all happening in complex numbers. So this meaning of a square root, it has to be carefully thought out. But let me use this real example to see what we are about to do. The z squared plus w squared equals 1. And if these were real variables, it's going to be a circle. So I'm going to use this circle in here. This is top half of the circle, missing this endpoint. And there is this x-axis. Every time you have x-axis in here, and you can send it to one of the points in the circle. And this is geometric, but if you write down the map, it's differentiable map and things like that. So what this accomplishes is that line segmented down in the x-axis, and we create a differential map to this curved object that's sitting inside two-dimensional space. So we can kind of pretend that we understand, we can see this world, but we cannot see this world. But we can do algebra and analysis so that we created this nice one-to-one differential map. The other half of the circle looks like this, and x-axis is here, doing the same thing and send it down, and that's what this map is about. Then we create the same copy of x-axis is mapped to lower half of the circle. And I'm going to call that one S1 and S2. Then knowing that by not being able to see this one, we can still calculate this one is going inside a one-to-one, and that one is going inside a one-to-one, and they're disjoint. And they carefully analyze it under this map where this tip points goes. They realize they're going to the same point, so they realize that this thing and that thing in that space, in a two-dimensional space we're pretending they can't see, they're putting it together, but there's no overlap here, just that end part. So maybe you can figure, all right, there's one, and we can't overlap, and there's the other curve must sitting inside another other part. So, and then you fill in that part that we ignored, and the end part they join together like this. So, kind of have a little rough picture of homeomorphism classes of what we're embedding in here. Something like this will happen. It's more complicated. So let me show you the next picture. So here is a complex situation. So you look at this map, you consider one complex number and sending into the upper half plane in the real variable situation. But you can't see it, it's here. So you construct this map. So you have one complex variable in here. You send it into s goes to s, and the other variable w becomes square root of 1 minus s squared. And this is simple, s going to s, but this one you have to look carefully at what's really happening, and you have to make sure this is analytic in here. And to make an to make the map analytic with this choice of square root, and we realize that you have to get rid of these cuts. It's called branch cuts. So without that lines in there on all the other things, and the map is analytic mapping in here, just like the early example. So the next one is going to be exactly the same thing, but slightly different. What it changed here is that I just index it differently. Another thing is that the same map, complex numbers in this exact same copy is going to S, but here with a negative. So we created one copy of C0 going inside S, another copy of going inside S. And then you have to figure out if they intersect or not. But it turns out it's disjoint. There's a C0 going in there, another copy of a C0 going in there, but they don't intersect. It's disjoint. So somewhat, one copy of this going in there, another copy of that going in there, and this slit, this branch cut, is joined together and complete this picture. So I'm going to actually do some deformation or little a holomorphic map. So here's a C01 copy, and I'd like to claim that this is holomorphic to the following region. This can be done by something called the Riemann mapping theorem. So in this region and here, simply connected region can go into that simply connected region, and this is homeomorphic. And there's another copy in there, so that another copy goes exactly like that. So this level is map is done holomorphically in the next level, and I'm going to put these two things together, and that's the homeomorphic level. So you look at this this slit here in the neighborhood of those points and see where they're going into in that space, and carefully. And it turns out these two things, these borders and open borders, and put together and create open cylinder with infinite open cylinder and open to this side and that side. So this is homeomorphic level. So all I'm saying here is that that Riemann surface I call is homeomorphically equal to that open infinite cylinder. That's one way to look at this one as a topological object. Next one is really winner. Let me show the next one. It's exactly the same problem. Look at it in a slightly different way. This one we never factored it before, but now we're in a complex number. You can factor it using this I. So once you factor like this, it's a typical parameterization of a hyperbola. So U is going to be that first number, Z plus IW. And the other number must be 1 over U. There's no choices. It's 1 over U there. And this is going to be Z minus IW. Then by adding these two things, you get 2Z, and this cancels. So it turns out Z is 1/2 of U plus 1 over U. W is if you subtract these two, and you have 2I as a coefficient, and U minus 1 over U. That's the parameterization. See, the Z and W that's in here, this Riemann surface, now completely parameterized by one variable. This is typical rational parameterization of hyperbola. But the problem is that U right here is not defined when U is 0. So you look at the entire complex plane and just subtract that one point in that so that this thing is defined. Then it turns out this map from U variable going into ZW in that way creates biholomorphic map. Okay, so let me explain in a better way. So what we have created here is a C minus 0, the punctured plane. Here's a 1, 0, and everything else is there, solid and not changed. Everything is there. And then there is this S that's sitting inside a 4-dimensional real space. We can't visualize, but we created biholomorphic map in such a way that these two things are identified as a same object in this biholomorphism class. And this is really, I didn't bent around anything, it's really solid just map. So this really represent this complex analytic structure under this map is exactly preserved in here. Which is a punctured plane. Now let's look at the next example. Next example, I raise the power to another level. Then again, it's happening in a complex plane. Then it's because it's a simple cubic equation, you can isolate W using the third rooted in complex numbers. And then you have to go through complicated branch cuts and try to glue them together. And there are 3 pieces or 2, whatever. Anyway, after you glue them together, I'm using this one wiggly symbol for homeomorphism class, and it turns out this thing is homeomorphic to this donut with one little hole in there that corresponds to open unbounded region in there. But you can kind of close it up and homeomorphically represent this one donut with a 1 point missing that corresponds to this open end. And this quality there's this donut and there's this hole in there is called handle, and that's the term in mathematics, and this is called a genus. If you see one handle in there, it's a genus 1. So let me picture, this is homeomorphically equal to this shape in there. But we didn't discuss anything about complex analytic structure, but homeomorphically, here's another picture of genus 2 case. This is a simple case. Let me draw the complicated case, which is also considered as genus 2, but looks more complicated. So here's challenge. So here's one ring is connected around there, and here's another ring, and then it's connected in there. There's another donut around there. I already missed that, so I'm going to erase that and redo that part. It has to be connected with the other one, connected the other one there. So there is that. Donuts. Hope you can see that. There's one donut that coming from in here, but somewhat this is, cut out and re-glued and back in there. This operation cannot be done in 3-dimensional space, but if you put that one into 4-dimensional space and nicely bring it inside and project it down to this one again, and their homeomorphism can be lifted to, in this higher dimensional space, actually homotopically, continuously can be done. But these are also called genus 2, and homeomorphism class doesn't distinguish this from that. They're all the same thing. And Riemann classified all the homeomorphism classes of all the Riemann surfaces, orientable Riemann surfaces, into everything. All the genus 1 is homeomorphic to that. All the genus 2 is homeomorphic to one class. So completely classified up to the genus. Right, now it's time to look at the good definition, not just example, and what is a Riemann surface. And there's a typical definition that it's given there using chart, but I'm just going to skip that part and go directly to, this is my favorite definition, this metric definition. So I wrote here is a topological space S of genus 2, and that's the picture, like I said, and they're all, maybe there's a holes in there, but they're all homeomorphic to this one. So there's only one homeomorphism class in there. What about Riemann surfaces? Riemann surfaces are more than just homomorphism classes. So you have to put this complex analytic structure in there. But it can be done in the following ways. Let me draw another genus 2 curve, and it looks, and suppose this looks slightly different, and this has a genus 2, and that also has genus 2. It's topological space. There's no complex structure in there. But this one really coming from, for example, x to the n plus y, and z to the n plus, w to the n equals 1. Let's say the genus 2, and they're coming from there. So we have created this homeomorphic map in there. Okay, what now? This one doesn't have any complex structure in there. This guy has a complex structure. So maybe this is sitting inside some 3-dimensional space, for example, like that. How do we put this complex structure on it? Using this homeomorphic map. So for example, if I take the little curve on that genus 2 curve and you map it through that, it turns out it's pretty short in there. So if someone is looking at this short curve on this topological space, someone will say this length is just 1. But we're not going to say this length is 1. We're going to use new metric. New metric is coming from this structure here. So suppose this is homeomorphic map. Then maybe that length here is 4 times than that. So this length is now, this is going to get a new length in here, 4. Okay, so maybe if you look at it here, there's a long curve in there, but if you do the inverse image, maybe that's very short in here. So instead of doing that, that's like length 8 compared to that, length 6 compared to that. No, you have to actually look at it here. It's going to be length 1. So which one, this length function in here is completely rewritten through this map. So I'm going to give you a very simple example of how this can be happening like this. So next example in here is this one. It's a very simple example, and it explains a whole lot. What we're going to look at here is this first quadrant in here, and in here we're going to look at this entire upper half plane. If you square it, this first quadrant is going to go to complex holomorphically go to the entire upper half plane, which is called H, the standard notation for that. Then we can look at this circle, starts at 2, ends up in 2i in there. And if you send that along the square map, it's going to go to 4 if you square that. If you square that, it becomes a negative 4. And this whole circle remains a circle, miraculously, and making this bigger circle. Now, if you look at this arc in this typical complex plane, if you ask them what the length of this one is, everybody will go, it's a half of the circumference, 2 pi, of the radius r. So that's 4 pi. So length of this one is a 4 pi. Now, we're going to put a new metric, whatever the mechanism or mathematically right way to do that. The answer is really coming from here. We're not going to call that as a length 4i. We're going to actually use this length in here and call that as a new length for that one. So let's compute this one. This is 1/4 of 2 pi of the radius 2. So they all cancel, become just a pi. So according to the new metric, which is completely determined by this complex analytic map, then this new length is going to be just a pi, not 4 pi. So the ratio is 4 here, the 4 times, but it is not so. If you go over here, maybe ratio is going to be slightly different. Everywhere, the way it is stretched apart is constantly varying as you move around. So that's the new metric. And this metric is called Riemannian metric. And this became important thing. It gives you the right idea and a framework and a foundation for the modern physics, such as the general relativity. Here's another standard example. Here is a whole complex plane and viewed from a three-dimensional perspective. This is, we're just looking at the topological space in there. Topological space. We're about to give a new metric. So we're going to map it and create a new metric in there. All right. So the idea of the map is this one. The thing that we're looking at is the sphere in here, and we map it from each other point. So I choose one point in the complex plane and connect it to the North Pole. And you can see that it always is exactly one point on the sphere. So this gives you one-to-one correspondence. So this point in the equator is the same point. It's on the sphere, it's on the plane, and it fits into that description. I just described how to make this one-to-one correspondence. If you happen to have a point inside there, inside the circle, if you connect it, and you pass through, go underneath it, and find the point underneath that sphere. All right, that's the idea. Now, this Riemann, this sphere is called the Riemann sphere. It has its own metric. For example, this circle here is a common part of this thing, so we have exactly the same thing in here. Same circle, this equator. But this time I want you to look at the little circle on the top of this sphere. The length of this one is much smaller than that, right? But under this projected image, this circle, you can see this actually goes a lot wider there. So the images of this tiny circle around the North Pole through this projection idea is really big. So out there is a big circle out there. So usual metric of the sea, this is going to be a really long arc. But we're not going to use that metric. We're going to use a new metric that is coming from this Riemann sphere. And that one is fairly small. So actual arc length of this one is going to be considered smaller than this one, according to the new metric. And that's the idea. So let me give you actually a better description than this type of a metric idea is the following. It is relying on following idea. Suppose you have a curve maybe on that sea. This is how we calculate the length of a curve. First, you come up with a parameterization and you divide it into in a segment like that, and you look at this part and calculate tangent vector, the velocity vector, using your parameterization. Then we're going to compute the length of that parameterization and multiply by the segment you're using for your parameter. Do the Riemann sum, and that's going to be the arc length. So we're going to rewrite this absolute value part using more linear algebraic term, namely square root of this tangent vector, velocity vector, dotted to itself. So here's a dot product. So we're saying the length of this one is done through the dot product. So the idea is this new metric, we're going to look at the idea for the new metric is the following. If you have a one point in there, if the curve's passing through there, there is this tangent vectors always. It's not really sticking out from the, they're actually on that plane. 1, 2 vector in V and W like that. And if we can redefine this dot product to be something else, and this whole machinery can be, we can go through that. So what is a generalization of a dot product? It's called inner product. If you have two tangent vector, and we're defining this inner product in here. Okay, so you look at this map carefully and do all the calculation. It turns out it is quite similar to usual dot product in this two-dimensional vector space. You're just going to scale it in a certain way. That scalar is 1 plus absolute value of z, the complex number, divided by 2. And there's -2 business in there. So usual dot product scaled by slightly different number, and as z is different places, this scalar is slightly different. And because it is still having that v dot w, it's going to have this conformal structure. The angle between these two things in here, after you map it down underneath it, the angle between these two things is going to be the same, not just a 90 degree. So the conformal structure is there. That is a important part of a complex analytic structure. If you look at complex map between C to C and the Jacobian level, all that is a stretching and a rotation. So this really captures this complex analytic structure. So if Z is really large, it's out there something like that, its inside is big and it's -2, you can see qualitatively as you go out, and these things are considered very small. So that's actually how the Riemannian metric is defined. Every point we define the dot product, redefine the dot product to some sort of inner product, and it is not uniform as you go around. They're all different. Here's one last, and it is a very important example. So we looked at that particular metric and just flip that positive sign to negative sign and see what we get. For example, so we have this, and this dot product or inner product must give you the positive definite kind of condition. So we have to keep this one as a positive number. That makes this absolute value of z less than equal to, actually less than 2, positive definite to be less than 2. So this metric will only make sense within this unit disk and not unit disk, a disk of radius 2. So we have a certain metric in there. And it is represented here. This is called Poincaré's disk, and also the geometry created by this metric system here is called hyperbolic geometry. And this is the first non-Euclidean geometry discovered by Gauss and Bolyai, the Hungarian guy, I think, and those people. So let me explain what this line here is. This line is kind of describing how it looks like, and it describes how this is bent around. This is called a geodesic. So let me explain what the geodesics are. Geodesics are, if you look at this line, so we're going to put a little tiny neighborhood around it. And starting here and there, that doesn't change. But think about deforming that curve a little bit in there, like this. As you deform that, according to this metric, the length of this metric is going to change. But there's a small neighborhood, and this line that they have sketched, and you have the property that it has the shortest length starting from here to there, locally. Globally, it's not the shortest path, but locally around, there's no deformation. Deformation will improve arc length of going from here to there. That is called the geodesic, and it's geodesic is an important idea used in general relativity, and in the modern physics, it becomes an important thing. Anyway, those are the geodesics, kind of locally the shortest path, and then put them together. And again, that doesn't mean starting from here to there, and this is the shortest path, but locally we have that property. All right, these are the important 3 examples of Riemannian metric. Use similar topological space, and you define a very different type of geometry using deforming kind of this inner product in each of the tangent space. So here's some classification result. Here's a simply connected Riemann surfaces, and there are three kinds: Riemann sphere, and the complex plane with that usual complex analytic structure in there, and the Poincare disk that I showed you. And this has a conformal structure from analytic structure, so that makes an analytic structure. Another important thing that is attached to the theory of surfaces, when we look at the real surface or two-dimensional real manifold, is this Gaussian curvature. Gaussian curvature is usually denoted by a capital K, and this is the curvature for a surface, and Gauss's work on is called the remarkable theorem. Gauss's remarkable theorem on the curvature, and this curvature is preserved through this isometry, the map that preserved the Riemannian metric, and this curvature is preserved, and that was a greatest accomplishment. That's something that is preserved through this intrinsic geometry. And Riemann was a student of Gauss, and Gauss actually asked him to generalize this phenomenon. Riemann, who actually did generalize, so he created, defined the Riemannian curvature, and that became the foundation of the curvature that is used in general relativity, Einstein's curvature, and things like that. So it's an important part. So we're going to look at the curvature. This turns out the Riemann sphere, the one that we just showed, you earlier, has the constant curvature everywhere. The Gaussian curvature is 1. This one is a flat one, so the Gaussian curvature is 0. Poincare disk, it turns out the Gaussian curvature is exactly -1. So let me tell you the typical example of positive curvature shape. So if you have a surface and there's this normal vector space in there, all around the neighborhood, if the curve is kind of bent away from the normal vector space, normal vector, then it's a positive curvature in that. So if this looks like a piece from the Riemann sphere, and this is perfectly flat, and that's an example, good example. And -1 is the following shape. This is a saddle shape in here. I'm sketching it here. It's a saddle. All right. So that saddle point in there has that property. So if you put that normal vector, if you look in one way, this kind of curve is going toward that normal vector. But if you look at the other direction, it's kind of moving away from that normal vector. So if these two things are happening, this is a typical characteristic of Gaussian curvature -1. Also, these guys have a constant curvature. Anywhere you look at it, this Gaussian curvature is always the same. The following is called the Riemannian mapping theorem, or in general, it's called the uniformization theorem. Is the following. Okay, I deleted the whole thing. Let me say that again. So if I have simply connected Riemann surface, and so it's not going to have several genus, it's going to be just simply connected. It can the genus 0, that must be the case. But this classification theorem says there's a biholomorphic map such that given any simply connected Riemann surface is either biholomorphic to Riemann sphere or biholomorphic to complex plane or Poincare disk. So all these, the three things are pretty much it for up to complex analytic isomorphisms. In the next level, and I think I've already talked about, let me go to make sure I talked about the curvature. Okay, I did talk about the thing. So the next level is that of classification is not through the simply connected Riemann surfaces, but in terms of the Gaussian curvature. So the surprising thing happens. So let's see. So the classification by curvature. So this is a constant curvature 1 and constant curvature 0 and constant curvature -1. So this is the full uniformization theorem. Uniformization theorem. says, given any Riemann surface, simply connected or not, there is a biholomorphic map so that it is biholomorphic to a Riemann surface with a constant curvature 1, or a constant curvature 0, or the constant curvature -1. So that's the theorem. And if you look at this constant curvature 1 and constant curvature 0, there are not too many, so we're going to list them. Curvature 1 is a Riemann sphere. We already saw that. Well, this is general Riemann surface. Maybe it has some holes in there and things like that. But it turns out this is it. All the other Riemann surfaces with the positive curvature is actually biholomorphic to this Riemann sphere. That's the only one. K equals 0, flat one, we've already seen that as complex plane. And another one we saw that was z squared plus w squared equals 1. That's holomorphic to the punctured plane. And one last one is complex Riemann surface with one handle. Maybe it had some holes here and there if it's not compact and things like that. But under biholomorphic map, they're all isomorphic to that. And these are all have a constant curvature, one that has a constant curvature. -1 is there are a lot of them, abundant examples are there. And hyperbolic sources says that its classification is not possible, but partially can be done. A Poincaré's disk is one example we looked at in here. Okay, so this particular one in here, Riemann surface with the negative curvature in here, that one is called hyperbolic surfaces. All the curves with a genus greater than or equal to 1, and it has a hyperbolic structure in there. Genus 1 appeared in this k equals 0 space. So Mirzakhani's work is about these hyperbolic surfaces. So that concludes the introduction to the Riemann surfaces and mainly to hyperbolic surfaces. Next item is this called the moduli spaces. And we're going to look at example, but rough idea is that think about on having some geometric objects like triangles and planes or lines, but same kind collected in here, and there happened some one-to-one correspondence with this huge object. Similarly, it takes a lot of spaces to collect them actually and physically, so that kind of represent and what kind of thing that we're looking at in here. But on one side of here is a complex analytic algebraic variety, and let me just use an example like this. One complex variable and another complex variable and another complex variable and another complex variable. Maybe this is a polynomials. 4 variable of complex variable polynomial set equal to 0. Then you can think about, 1 point is a quadruple of complex number, so this is solution. 1 point in here in this one solution set correspond to each of the objects in here. And this idea is a moduli space. Again, we think of the collection of all the geometric objects we can think about and make a nice one-to-one correspondence with 1 point in the single equation, a polynomial equation. That space here is called moduli space. So we'll look at example to see that. The one example I thought about is the following, and I'm not going to go into details, but all the lines in R2. Here's one line in xy plane. Here's another line in xy plane. Here's another line in xy plane. Another line in xy plane. You can think about all the lines you collected in there. What could be the moduli space? All right. This will be just the homeomorphic description of the moduli space in here. But naturally, next step is that ax plus by plus c equals 0. All the lines in xy plane must have this shape of equation. Okay, so x and y are the main variable, so all that is this ABC. So we have to extract that ABC. So all the lines has this 3 coefficients assigned to it. So some of them, if you can think about it, and some of these triples actually represent the same line. That's what we have to think about. You can do it quickly, but we'll do the one step at a time. That if you look at positive number, if you multiply by positive 2 and positive 2 and positive 2 there, then you can see that's the same line. You can cancel those two factors of 2. So one way to look at it is if you look at this as a vector in three-dimensional space, the position vector, let me use P instead of that, position vector there, like this. Right? So it's a scalar, it doesn't matter. So maybe we can divide it by its own length. Okay, so rewrite it with ABC. Like that. So we're not looking at arbitrary ABC, we're looking at ABC that has length 1. So that looks like sphere. Any vector has length in three-dimensional vector length 1 is ABC is on this sphere in here. So what we accomplished here, all the lines can be mapped into that. So I'm going to call this curly L. So curly L, all the lines have somewhat identification in that space. It's not one-to-one yet, but it's there. So you have to be careful. When A and B are equal to 0, then C cannot be 0 anything else. If it is 0, it's not going to be a line, it's going to be an entire plane that satisfies that equation. So when A and B are 0, C cannot be anything. So when A and B are 0, there's just 2 points in top and bottom. You have to remove that. There's no corresponding to a line. So that's the one thing. We can remove that. Another thing is that if you look at this point in here, ABC, and the opposite point is a negative A, negative B, and negative C. If you multiply by it, that is called antipodal point. These 2 points actually, through the negative coefficient, is the same thing. But if you do the separated like this, positive coefficient and negative coefficient, now finally taking care of it, you kind of see that object and intermediate object and correctly identify this thing. All right, next part is maybe holomorphically or homeomorphically. I can turn this around, this open hole, turn this around, kind of exaggerate that hole like this, that open hole in there. So there's the surfaces, and here it's kind of, maybe I have to use this solid thing here as the front side. So I turn this one around and make that hole a little bit bigger. And this can be done homeomorphically. Holomorphically, not homeomorphic. It's homeomorphic on holomorphic. All right, so these boundaries are not part of our point. And you can kind of look at it as a kind of little cylinder to sideway. Point here, and there's antipodal point there. But they're all pretty much at the bottom except the sideline. So we can get rid of that bottom part like that. All the bottom is identified across in the top part. So you don't need that bottom part. So we're getting closer and closer injective in here. So no points in above of a part is identified together. So that's good. But the bottom, the equator part, and then here is across there identified. This one is identified to that. That one point here is identified across there. So when we try to kind of put these boundaries and that side together, and you end up at, gluing through like that. And this is a terrible picture of a Mobius strip, but we don't include that boundary. So open boundary Mobius strip, it seems like a one-to-one correspondence with sort of all the lines in there. So this is a homeomorphic description of the moduli space of all the lines in R2. All right, so that just gives you an idea of the moduli space. Most famous and well established moduli space example is perhaps the following. Elliptic curve. This doesn't have to be algebraic, just any compact Riemann surface with genus 1. Okay, those are called elliptic curves. And we're identifying up to holomorphic, biholomorphic map, so it's complex isomorphism classes. So that's our stuff in here. All the compact Riemann surfaces of genus 1. Okay, they can be holomorphically mapped to a constant curvature, but this is a constant curvature 0, but this is our the class is there. So I'm going to denote it like this. Elliptic curve, that's another different name of this Riemann surface of genus 1, and this is isomorphism classes. First thing they accomplish, it is long story short, is that upper half plane in here. This is a complex plane. Upper half plane has a standard notation, this curly h. So we have one complex number in upper half plane, usually denoted by tau, and all this surjectively going in there. All the isomorphism classes is mapped into one point in upper half plane. And there's it's not yet one-to-one. It turns out it's another one, tau prime, and that's in the upper half plane. They're actually correspond to an elliptic curve that are isomorphic to each other. So what is the connection? What is the relationship between these two complex numbers in upper half plane? It turns out that tau prime is a tau plus b divided by c tau plus d, where this a, b, c, d makes integer matrix with determinant 1, so-called SL2Z. So if this is called a Mobius transformation on complex numbers. So if you have one complex number, and under this Mobius transformation through this integer matrix with a determinant 1, if you reach by that, these two things actually correspond to an isomorphism class. So it turns out this completely describes it. So here is quotienting. The h, lots of point here h, is identified as same under this isomorphism classes idea of the isomorphism classes. And it turns out this is a collection of taus that are not related under this action. Stripped like this. The real part is 1/2, and the other one boundary is negative 1/2, and that is a part of the unit circle. So anything inside there cannot be reached under this action. Therefore, the one-to-one correspondence with elliptic curves. And this side and that side is identified the same. That point and that point is identified the same. And complex analytic biholomorphically, this one turns out to be exactly the same. The Riemann sphere with missing one hole. Okay, so done all. So what we have, what they have accomplished there, the isomorphism class of all the elliptic curve has a one-to-one correspondence with the Riemann sphere, and this one-to correspondence is done through some complex analytic map. It's not some homeomorphic artificial relation. There's a natural way of going back and forth. So that's one nice moduli space. Before we enter Mirzakhani's work, I have to emphasize and this following work in elliptic curves to show the audience what is its moduli spaces for. So here's one copy of the moduli space of elliptic curve. By taking one element in SL2Z, if you hit it, and it's going to create another copy. But suppose we chose it wisely so that this another copy is connected to that. And choose another one and hit it again. Maybe it's going to look like this. Really real picture, something like that. There's a certain way of generating the finitely many copies all connected like this and create a complex manifold in here. Turns out these guys has name. I'm going to use that name. A compactified version of this one is called modular curves, and there's just this n tells you how to create the copies in there. And this x0n given positive integers there is usually the Riemann surface, as you can see, is the pieces of upper half plane. So have positive genus. Usually could be genus 0, and it's a Riemann surface, compactified as compact Riemann surface. This name x0n. All right. So you can create the multiple copies, and there's a way to do that at given n. And this is something called Shimura theory. And given this modular curve, they were able to generate an elliptic curve and be able to create this complex analytic map from here to there. Not isomorphic, it could be a very big genus in here. But what has happened is that this one copy is naturally structured in here, is a moduli space of all elliptic curve. And there's several copies of that according to that rule, and then all of a sudden there's a map in there. So this is a one single elliptic curve associated to that. So if you want to study its elliptic curve, how many solutions are there, any algebraic or analytic or arithmetic questions about what is it about this elliptic curve, actually there's a bigger picture, and all the solution can be obtained by looking at this curve. And what is this curve? Is the entire class of elliptic curves. So in other words, some problem about one particular elliptic curve actually is tied to all the other elliptic curve. It's out there. It's interesting because you have to kind of look at all the other isomorphism classes of elliptic curves to answer this one particular elliptic curve. Well, I think this certainly explains what this moduli space is doing. And it is this amazing picture in there. Since we're here, I mentioned this Eikler-Shimura theorem, and the next theorem is called Taniyama-Shimura-Weil theorem. It was a conjecture before. It goes the following. If you pick an elliptic curve in here with rational coefficients, and if you enter algebraic curve, and suppose this one has algebraic curves with a rational coefficient, which is a number theory problem. Now if you have an elliptic curve, it's going backward. There is some modular curve in there, so they look crazy like this, jagged and shaped like that. Maybe it has a finite shape, something like that. This is again generated by finitely many copies of the original moduli space of elliptic curve put together, finite many of copy, and there is a map here. To the backward, given elliptic curve, there is a modular space, modular curve, which is copies of a moduli space mapped down there. So you really start from this curve and want to solve some arithmetic problem in there, since it's defined over with a coefficient in rational numbers. Then maybe you have to look at the copies of these moduli spaces, which is all the elliptic curves are put together, and they hold a key. And in fact, a lot of problems in a number theory actually uses this modular connection through the modular form. So this is a celebrated work in the 90s in mathematics, and Andrew Wiles and et al. Other people completely proved and this conjecture for all elliptic curves, and using that, and they were able to prove Fermat's last theorem, which is notorious problem in number theory. So this is an interesting picture again. So one elliptic curve, you have to actually look at the moduli space of the elliptic curve, and because there's a connection in there. So the work of Mirzakhani is kind of in that direction, and we're looking at one hyperbolic surface in here, and then we're counting something, but it turns out this counting is coming from the moduli space. Now finally, let me explain this one of her work. It's titled "The Growth of the Number of Simple Closed Geodesic." Well, I explained the geodesic. It's kind of locally shorted path. That's one way to look at it. It's a given metric. Simple means that there's no crossing in here. So if you cross it like that, it's not simple. And closed means, and you have to come back to where it started. So if I do that, it is closed, but it's not simple. But if I do this, then it's simple and closed. So those are the curve. Simple and closed is just a topological term. It doesn't require any metric. Geodesic requires metric in that. And hyperbolic surface is the metric term. And these are the surfaces that are biholomorphic to Riemann surface with a constant curvature, -1. Okay, this work really represents her initiative toward to the other works, and it was published in the Annals of Mathematics, 2008, and this is one of the most prestigious journal in pure mathematics. Since there are a wealth of examples in a modular curve with a genus height greater than 1, I use that picture in here. It's some sort of modular curve, but what we're looking at is a complete. That means algebra, in some algebraic sense, in algebraic geometry sense, it can be compactified. And that's this term in the meaning. And hyperbolic surfaces, we know what that means. I just explained that. And also has a finite area. I'm not expert in this area. I'm not sure if I know an example of hyperbolic surface, a finite area. I'm sure there's many of them, but those are the conditions. And here's an example I'm looking at in the upper half plane, and this is kind of obtained by function subgroup, quotient by the function subgroup of upper half plane. And SL2Z was one of the examples. Although the title does not specify what kind of hyperbolic surfaces she's considering, but that's the class of hyperbolic surface she's considering. So at this stage, let me explain her counting problem. So we have these surfaces in there, and she wanted to count simple and closed geodesic on this hyperbolic surface, for example, like that. So this is the inside is all different representative, but the boundary is actually glued together. Maybe it's going to glue it in a weird way like this. This is supposed to be orientable surface. There's no, so maybe it should go maybe in that direction. I feel more comfortable with that. So if the curve started like that and follow through the metric that was associated, it is not exactly the metric of the usual complex plane. Maybe it looks something like this. You end up in there. But this point and that point, it seems like a different point. But when you identify, when you glue this side, and this becomes the same part. So it's a closed part is satisfied, and simple part is not crossing here. So that's going to be simple. So that's one example. So that's a simple closed curve, kind of visualized in this arbitrary picture. And she wanted to count the following: given hyperbolic surface, you come up with a real number L, and we're going to look at simple and close the geodesic in that space X such that its length of that simple geodesic is less than or equal to L. Okay, so of course she's not looking for a closed formula of this one, but she's calculating asymptotic result of this one. So her asymptotic result is the following: the number of, which happens to be finite, of a simple closed geodesic with length less than or equal to L grows like this. If you divide that number by L to the 6g minus 6, and we'll explain where this 6g minus 6 is coming from, g is the genus of this x in there. All right, I was interrupted. Let me just continue. If you do that, this is accounting, and this is the kind of order of this growth. And if you do that, it converges to number n, and it's not necessarily integer. It's just the number that she uses. This is the result. So far, there's no moduli space. You look at the curve, and this is great result. And there was a result before that without the simple condition. It's just to close the curve like this. The same thing, close the geodesic and bounded by the length in here. And it was known that is asymptotic to e to the L, the exponential number, divided by L. So this grows a lot more than this polynomial growth. And this number was considered as a prime number theorem of the geodesic, since the growth is just like the prime number theorem. But if you look at the simple closed geodesics, and she gets this polynomial growth, and that's her work. Okay, so, and she obtained this result by looking at the moduli spaces of hyperbolic surfaces. So here's her idea. The moduli spaces we're entering is the following. First, if you look at the closest surface of a genus 1, this is a topological level. There's no metric sensitive term is involved. And if you look at this homeomorphism class, if I write down some sort of model and topological model, and here in upper half plane, every other closed surfaces of genus 1 greater than 1 is homeomorphic to that guy. So we use this topological space to describe all the other Riemann surfaces of genus, fixed genus that is greater than 1. So you use this, borrow this topological space and change the metric. So S is the topological structure name, and X is representing the metrics. Metric, the Riemannian metric is defined on there. So the rest of the part is to explain the connection to the moduli space. So I have to introduce some of the terms. And after I read it, it sounds technical. It's not too bad. Well, so with whatever we have discussed so far, that we can completely understand all the elements that is involved in this following formula. So first thing we're going to go through is multicurves. All right. So here's gamma I is a finitely many curve that are disjointed, that are not crossing each other. And this curve is just set theoretic or topological elements in there. But we're going to multiply by positive integer or negative integer or any integer AI and sum it up. And it has no meaning. This must be the formal object. But we consider this when you consider integral, a line integral, one curve and 2 times, things like that can be put into like this with a subscript in there. So although this is a formal sum, this summation structure is naturally behaving nicely with the integral. That's the motivation of this notation. So we look at all these formal sums called multicurve and extend the coefficient to the real number. Okay, this one, they call this one measured lamination. This is the collection of this formal object. And they define measure to this set. There's no topology or anything. It is just pure set. And they defined something called the Thurston measure, which is natural from this linear structure that is extended. That's one thing, multi-curve in there. Now, the next part is metric sensitive. There's no metric in here. It's just topological object. The first thing we look at is its length. Okay, whenever you introduce this metric to this fixed topological space, we have to use the subscript that's sensitive to the metric you're using for that space, and then put this multi-curve in there. Now, this can be now real numbers. So we're going to just naturally linearly extend this version. Of course, we have a meaning of this given actual curve because of the metric, it has length in there, and just to linearly extend and define things to be like this. So for all this multi-curve, we extend the meaning of the length to that multi-curve. Okay, next one is this bx. B subscript x, she introduces. This is all the multi-curves. So it is sitting inside this space here, measured lamination, such that its length is less than or equal to 1. It's like a unit ball. So this pure object is now having, because of this metric and the length function, becomes a little bit of a metric space itself. But that's what that is. So that's an object in there collected. And she defines B parenthesis x as this subset in that multicurve world, and she puts this Thurston measure of that collection of multicurve. So in short, this is the measure of pure subset, which are multicurves of length less than or equal to 1. Again, there's no moduli space yet, and this whole thing is calculated by just looking at one metric structure that's put on there. But this one is one of the things that's involved in that computing that asymptotic result. So where's the moduli space? Right, here's the entrance in the moduli space, and she uses moduli space as curly M. This is going to be all biholomorphic isomorphism class of all the hyperbolic surfaces of fixed genus G, and genus must be greater than 1. So that's the moduli space. And dimension of these thing turns out to be 6G minus 6. That's the order that we saw that in the asymptotic result. One other thing we'd like to introduce in here is this volume element, which is named there Weil-Petersson volume element. So if the theta won't represent a one form, if you keep wedging to different type of one form, and this might survive and being a non-zero, and that can be served as a volume form in there. Okay, so the all the volume form of this level of differential form is just up to scalar. So there's pretty much the unique volume form to this thing. I'm going to call this one just the psi. So what this means is that, let me use this cubic box to represent these high dimensional objects. For example, if G is 2, then it's going to be 6 dimensional object. Is that right? Yeah, 6 dimensional object. So the volume calculation is the volume of this in 6 dimensional objects. Let me pull out a little bit of space on the subset, which is still in 6 dimensional subset, and then we can think about the volume of this thing. The way it's calculated is through this volume element. Easiest way to visualize this volume element is using this matrix of 6G minus 6 by 6G minus 6. And this is just like that Jacobian matrix you see it in multivariable calculus level. And this matrix to take care of all different parameterization. So let me go back in here. This is some, let's say, 6-dimensional object. To calculate this volume, we often use the parameterization. So using that 6 parameters, you parameterize it. But there are many, many different ways to parameterize it. Every time you do that, different parameterization, when you try to calculate the volume through the integral, there is this matrix, the determinant of this matrix that takes care of different parameterization you use. So that's exactly what this volume form is doing. Okay, so let me summarize it here. So this M is a moduli space of all hyperbolic surfaces of genus fixed genus, and I call that psi as a one. What is it? The Weil-Petersson volume element, and she considers something like this. Moduli space, the entire moduli space is a dimension of 6G. Let me write it over here. Dimension of that moduli space is 6G minus 6, and if you take the 1 in here, that will be the volume if you multiply 1 to the volume element. So I'm not sure if it is finite or not, but she claims that and calculates that if you put this density of this measure, this was a Thurston measure of a multi-curves of, whose length is less than or equal to 1. We're integrating like this. So let me get this picture again. There is this moduli space, big dimension here. Each of the point actually correspond to the one hyperbolic biholomorphic isomorphism class of one hyperbolic surface. So you go through all the hyperbolic surface in here and integrate over that these values in there. And it turns out this is a finite number. Miracle. I think it seems like it's a big space. But that's the one thing. Let's see how this one is connected to the counting, and that's her work. Okay, let me explain that result again. This Sx, there's no moduli space for this one. It's all simple closed geodesic whose length is less than L, and divided by this magnitude, and L to the 6G minus 6 is simple monomial, and this one has nice behavior, it approaches N. So that's all done in one hyperbolic surface. Then it turns out is equal to some quantity that is coming from moduli space of this hyperbolic surface. And there's this rational number. C is coming from positive rational number, and the rest of the part is this Thurston measure of all multi-curves whose length is less than 1, and divided by this integral value, and this thing is integrated like this. So it's kind of a proportion, and this is like averages, this is finite. So it's kind of representing the average of this measure, Thurston measure, and this is a proportion to that Thurston measure, and multiplied by some rational number. So if you just look at these two results, then this is one real number, and that's another real number, and there must be always a one real number. That's a silly result, but the fact that this being remain in rational number is really significant. And also, of course, if you look at her work of making this connection, it really reveals and how is this counting problem in here in this fixed hyperbolic surface is connected to something that's coming from the moduli space, the entire collection of hyperbolic surfaces in there. So in that way, it's somewhat analogous to what happened to the moduli space of elliptic curves. So to summarize it again, this counting problem in one fixed hyperbolic surface, its answer is actually reside in moduli space in the bigger space in there. It's very cool. So after that work, and then she used a framework on that, this trick of counting things in using this moduli space, and she uses that to come up with a new proof of Edward Witten's conjecture. I don't really know this, but I'm just copying from a note, and that was very well written. And this was about physical meaning of intersections of certain loci within that moduli space we talked about. Okay, so this is not anymore hyperbolic surface. Just we're looking at there's some loci in there in a big space with a dimension 6g minus 6. And this was Edward Witten is also a Fields Medalist, and who proved that conjecture for the first time. Kontsevich is also a Fields Medalist. I'm sure he got the Fields Medal for proving this work, and she provides a new proof and can kind of sense that power of her method. And after that, and she goes actually into that moduli space, not just looking at one fixed and hyperbolic surface. You go to the moduli space and prove another type of counting of a closed geodesic in there, like another prime number theorem in closed geodesics, not in hyperbolic surface, but in a moduli space. Okay, so at this stage, and according to that note I read, that this is really difficult, and no one really have an idea to what to do in that moduli space, and very little is understood by the moduli space, and this is considered as a great work. And even this third work is really celebrated among experts, and I guess she got her recognition in here, and at that stage and here she was really celebrated and became really a master. So this is about non-closed geodesic in the moduli space. I forgot to put in there, not in hyperbolic surface. So maybe in that moduli space you start in here a certain direction. That's how the geodesic starts. It keeps going, and it's just no stopping. The geodesic just keeps going, and maybe it doesn't end it like that. To keep going like forever. You can kind of imagine in this buccal surface in there, and if you start it in there, even in the cylinder, you can create it. And if you look at the cylinder, if you have a certain direction in there, it goes forever and it is non-closed geodesic. So if you look at the non-closed geodesic in this big moduli space, there's nothing we can say intelligent about it. It's erratic and chaotic behavior, and that's the consensus back then. But it seems like what she did is that the following, and instead of this idea of a geodesic, although is happening in a complex structure, is geodesic. It's really parameterized by one real variable, in the complex surfaces, but should consider something like a complex geodesics. And my guess is that it's probably geodesic using the complex variable, and there is a lot of regularities in there. I don't have a specific precise statement about that, but they're celebrating a lot, and this is a really great result in showing a lot about moduli space. Again, to understanding the geodesics in the metric space is the fundamental thing to do, and these two things really puts into position of a master in handling the moduli space of hyperbolic surfaces. So this kind of summarizes the work of the Professor Mirzakhani. Thanks for listening.